So, um, I want you to imagine for just a second that you're sitting on your couch, right? And you just send on a quick message to a colleague across the country. Or, maybe you click a link to stream a 4K video.
Right. Something we all do 100 times a day.
Exactly. And to you, it feels instantaneous. It's just a tap of a glass screen, a tiny microscopic pause, and the data is just there.
Yeah. It's basically magic to most people.
But underneath that glassy surface, there's this invisible, incredibly complex, basically microscopic postal service.
Yeah.
And it is executing millions of calculated decisions in the blink of an eye.
It really is. I mean, we are so conditioned to expect this immediate digital gratification that we tend to completely ignore the sheer physical and logical infrastructure making it all possible.
Yeah.
We just assume the internet knows how to get our data from point A to point B. But getting a piece of data across the world requires this highly orchestrated sequence of events. Like, it relies on very specific rules to avoid complete gridlock.
Which is the core of our deep dive today. We're looking at a stack of technical materials, specifically a slide deck designed for networking students who are studying for their CCNA certification.
Oh, the classic CCNA.
Yep, the gold standard. But we're focusing entirely on OSI Layer 3, the network layer. For anyone who follows networking, you already know Layer 3 is the domain of IP addresses and routers. But, we are going to look at the actual mechanics of this layer.
Right, shortcutting all that heavy jargon.
Exactly. We're moving past the textbook definitions to examine the engineering logic that actually allows the internet to function at such an absurd scale.
Yeah, and to set the stage here, the source material highlights that this network layer performs 4 foundational operations to make end-to-end communication possible. You've got addressing, encapsulation, routing, and de-encapsulation.
Okay, so a 4-step pipeline.
Basically, yeah. But what stands out isn't just that these steps exist, it's how agnostic they are. I mean, layer-by-layer encapsulation means the network layer literally doesn't care if the payload is a secure banking transaction or just a cat meme.
It's all just data to Layer 3.
Right. The IP header simply wraps the transport layer segment, slaps on the logical addressing, hands it off to a router, and then strips that header away at the final destination.
And the efficiency of that pipeline is what makes global routing possible.
Mm-hmm.
But to understand the anatomy of those data packets, we really have to look at the philosophy of how they travel.
Yeah, the underlying rules.
Right, the foundational protocol of the internet. IP, or Internet Protocol, is strictly connectionless. The deck uses this analogy that sending data over IP is essentially like walking up to a street mailbox and just dropping a letter inside.
That's actually a really perfect way to visualize it.
You don't establish a session with the recipient first to warn them it's coming.
Sure.
You don't, verify if their local mailbox is already stuffed full. You just drop it in and walk away.
Right, because there is no initial handshake, there's no pre-established connection, which means IP is inherently what networking engineers categorize as a best effort protocol.
Best effort.
Yeah, best effort. It operates with absolutely no delivery guarantees at Layer 3.
Wait, really? None?
None. If a packet gets dropped because a router's buffer is overwhelmed during, like, a sudden traffic spike, or maybe a fiber line gets severed out in the real world, IP does not attempt to recover those lost packets.
Oh, wow.
It doesn't track them and has absolutely no mechanism to resend them.
Okay, I look at best effort, and honestly, I see a lazy protocol. I mean, if Layer 3 is dropping packets the second a router gets congested, how is my real-time video call not just a stuttering mess?
That's a fair question.
Right. It seems like if the core protocol of the internet is inherently unreliable, the entire system should just be a chaotic void of lost data. Is Layer 4 just doing all the heavy lifting to fix IP's mistakes, or what?
That is a very perceptive way to frame it, actually.
Right.
And you're touching on a fundamental design choice of the TCP IP suite. In networking, unreliable is actually synonymous with low overhead.
Oh, okay. So it's about speed.
Exactly. IP was designed to be lean and incredibly fast. If the IP protocol had to pause, track and verify the delivery acknowledgement of every single microscopic packet before forwarding the next one.
Oh, the latency would be terrible.
It would be catastrophic. The overhead required for a router to maintain state information for billions of individual packets would just crash the hardware.
So the lack of reliability is a feature, not a bug.
Yes.
It intentionally offloads the babysitting, basically, to transport protocols like TCP. And TCP acts as the certified mail system to ensure order delivery. while IP just focuses on being the fastest possible delivery truck.
Exactly. And furthermore, for real-time applications like that video call you mentioned, the network actively leverages this lean design.
How so?
Well, video and voice traffic actually use UDP at layer 4, which is also connectionless. Because in real-time comms, late data is worse than lost data.
Well, because if I'm talking to you, I don't care about a frame from 3 seconds ago.
Right. You don't want a router pausing your live conversation to resend a dropped frame from 2 seconds ago. It would ruin the flow. Plus, modern IP headers utilize the differentiated services code point or DSCP field.
Okay, DSCP.
Yeah, it allows routers to implement quality of service so they
Okay.
can look at that IP packet and prioritize the live video call over, say, a background file download.
Okay, that makes a lot of sense. And another characteristic that keeps IP so efficient is that it's media independent, right?
Yes, absolutely.
Like an IP packet might start its journey as an electrical payload traversing a copper Ethernet cable in your home office. It hits a local gateway, gets converted into pulses of light shooting through fiber optic cables under the street,
Right.
and eventually becomes radio waves, broadcasting from a cell tower to a smartphone. Through all of those physical layer 1 and layer 2 transformations, the layer 3 IP packet, the internal envelope basically, it remains completely intact and unchanged.
Yeah, the router only strips away the layer 2 Ethernet or Wi-Fi frame to expose the IP header, reads the destination, and then repackages it into a new layer 2 frame suitable for the next physical medium.
So the IP envelope itself is untouched.
Untouched.
Let's examine that envelope then, because the source material breaks down exactly what is written on the outside of an IPv4 packet header. It's this block of data attached to the front of the payload, ranging from 20 to 60 bytes in size.
Depending on whether optional features are used, yeah.
Right, so we have the obvious fields like the 32-bit source IP address and the destination IP address. We also have the protocol field, which basically acts as an internal routing tag.
It tells the receiving computer's network stack whether to hand the decapsulated payload over to ICMP, TCP, UDP, or, another protocol.
So the receiving device relies entirely on that protocol field to understand the context of the payload.
Exactly. It's a really elegant way to maintain the separation of the OSI layers.
Now, while I was reviewing the deck, the field that caught my attention most was the TTL, the time to live field.
Oh, yes, the TTL.
It operates almost like a sci-fi self-destruct sequence attached to every piece of data on the internet.
That's a great way to put it.
It's an 8-bit field holding a value between 0 and 255. When a host generates a packet, it sets an initial TTL, say 64 or maybe 128, and every time that packet hops through a router on its way across the internet, the router is mandated by the protocol to open the header, inspect the TTL, and decrement it by 1.
Right, and that decrementing TTL is one of the most vital fail-safes in all of network engineering.
Because without it, routing loops would just destroy the internet, wouldn't they?
They absolutely would.
I was mapping out the logic, and if an administrator accidentally configures a static routing loop, say router A forwards to router B, B forwards to C, and C accidentally sends it right back to A, that packet would be trapped.
Yep, caught in a loop.
And without a TTL, millions of these trapped packets would just endlessly circle the globe. They'd infinitely compound until they consumed 100% of the available bandwidth and ground the physical links to a halt.
They would become immortal packets.
Immortal packets.
Yeah, but by enforcing the TTL, if a router decrements the value and it finally hits 0, the router immediately drops the packet. It just purges it from the network.
It just executes it.
Yep. And then it will generate an ICMP time-exceeded message and send that back to the original source address. That effectively notifies the sender that the path is broken.
It's basically a self-cleaning mechanism for the internet's pipes.
It's brilliant engineering.
It is brilliant. But as robust as IPv4 is, the source material focuses heavily on its fatal mathematical flaw, which is address depletion.
Yeah, the big IPv4 problem.
Right, a 32-bit address space limits us to roughly 4.3 billion unique public IP addresses. In the 1980s, I guess that seemed inexhaustible.
Yeah, back then.
But today, 4.3 billion doesn't even cover the smartphones in use, let alone servers, laptops, IoT devices, smart fridges. And the industry's stopgap measure was NAT, Network Address Translation.
Right, NAT, and specifically PAY, Port Address Translation. They fundamentally altered how the internet operates. To conserve public addresses, ISPs began assigning just one single globally routable IPv4 address to an entire home or a business.
Just one for the whole house.
Exactly. And the local gateway router then establishes a private subnet internally, like, your typical 192.168
Right.
network.
Right.
The router acts as an intermediary. It translates the private internal IPs to the single public IP by modifying the source ports on the packets as they leave the network. And then it reverse translates them when the response returns.
So it's essentially a corporate mailroom. The building has one public street address, and the mailroom intercepts the incoming mail and sorts it out to all the private internal office numbers based on a ledger they keep.
That's a perfect analogy.
It kept the internet functioning, obviously. But the deck notes that NAT adds significant processing latency because the router literally has to crack open the packet and rewrite the header on the fly.
Yeah, it's very resource intensive.
And it also fundamentally breaks true end-to-end connectivity between hosts, doesn't it?
It does, which is exactly why NAT was only ever intended as a temporary bandage. The permanent architectural fix is IPv6.
Ah, IPv6.
Yeah. By moving to a 128-bit hierarchical address space, IPv6 offers 340 undecillion addresses.
340 undecillion. The visual they use in the presentation is striking. If IPv4's 4.3 billion addresses were the size of a golf ball, IPv6's address space is roughly equivalent to the volume of the entire planet Earth.
It's almost incomprehensible.
It really is. It's enough to assign a unique IP to trillions of devices for centuries, basically rendering NAT completely obsolete.
And beyond just solving the sheer volume problem, IPv6 fundamentally redesigned the packet header for modern hardware.
Oh, right, because of the processing issues.
Exactly. The variable 20 to 60 byte length of an IPv4 header is a processing nightmare for modern routers. Variable headers force the router's processor to do extra math just to determine where the header ends and the payload begins. It consumes a lot of unnecessary CPU cycles.
So IPv6 strips out the less critical fields, like the checksum, and uses a simplified fixed 40-byte header.
Fixed at 40 bytes, yes.
And I imagine that fixed size means hardware routers can process IPv6 packets at line read speed. They can rely on specialized ASIC chips rather than software processing, right? Because the hardware knows exactly where the data payload begins every single time.
That is the crucial advantage. ASICs, or application-specific integrated circuits, they thrive on predictable, fixed-length data structures. IPv6 allows these silicon chips to route packets exponentially faster than IPv4 ever could.
So we have this streamlined, self-destructing IPv6 packet ready to go. But, before it can drop its TTL counter across the internet, it's still stuck inside my laptop's network interface card.
True.
How does it physically escape the machine? This brings us to host routing. Every single end device has to make an independent routing decision before a packet ever hits a copper or fiber wire.
Yeah, the host operating system maintains its own routing table. When an application generates a packet, the host network stack analyzes the destination IP address and compares it against 3 primary pathways.
Okay, let's go through those. First, it can route to itself using the loopback interface.
Yeah.
In IPv4, this is the 127.0.0.0.0 range, usually 127.0.0.1, or simply 0.1 in IPv6.
Right, the loopback.
Sending a ping to the loopback address never touches the physical network interface, does it? It just travels down the internal TCP IP software stack and bounces back up.
Exactly. It's an internal diagnostic to verify the host's local networking components are actually functioning.
And the second pathway.
The second pathway is local routing. The host calculates its own subnet mask against the destination IP. If it determines the destination resides on the exact same local network segment, it doesn't need a router at all.
Oh, it just talks directly to it.
Right. It will use layer 2 protocols like ARP, the address resolution protocol, to find the local MMANCI address of the destination device and send the frame directly across the local switch.
And the third pathway is remote routing, which actually requires the default gateway.
Yes.
The deck uses this room and doorway analogy. Your local subnet is a room. You can talk to anyone else in the room directly. But if the destination IP is on a remote network, in a different room or a different country, you have to find the doorway out.
And the default gateway is that doorway.
Right. Without a default gateway configured, or if the gateway goes offline, the host is trapped. It can communicate locally, but traffic physically cannot leave the subnet.
And you can actually view this logic in action on any modern operating system.
Really?
Yeah. By opening a command prompt or a terminal and just typing route print or netstat-r, you can examine the host routing table yourself.
I actually pulled this up while going through the notes. It outputs this matrix showing the network destination, the net mask, the gateway needed to reach it, and the specific interface card on the machine.
Did you notice the metric column?
I did. There's a metric column. I noticed that if the machine has both a Wi-Fi connection and a hardwired Ethernet connection, it uses that metric number to prefer the Ethernet path because the metric value is lower.
Yeah.
And that represents a faster or more reliable physical link.
The host will consistently choose the route with the lowest metric. So once the host decides the traffic is remote, it encapsulates the IP packet inside a Layer 2 frame addressed to the MA's address of the default gateway, and it transmits it.
So once that packet passes through the local doorway, it hits the provider routers. And this is where the sheer scale of internet routing takes over.
Oh yeah, the backbone.
When a massive backbone router receives an IP packet, it de-encapsulates the Layer 2 frame to expose the destination IP. But, with billions of potential destinations,
Right.
it has to parse its routing table.
And it has to do it instantly.
Right. I was looking at how these tables function, and I noticed routers don't just look for any general match. They search for the longest prefix match.
That's right.
It's essentially prioritizing the most specific set of routing bits from left to right. Correct. Like a postal worker choosing a direct street address over a generic zip code.
The longest prefix match is the fundamental rule of IP routing. If a router's table contains a broad default route summarizing an entire country, but it also contains a highly specific route pointing to a single corporate subnet within that country,
Okay.
and the incoming packet is destined for that corporate subnet, the router will always forward it based on the specific route. The longest string of matching bits wins.
Got it. And the routing tables categorize how they learn these prefixes too. When you log into a Cisco router and issue a show iproute command, the output tags every entry with a letter code.
Yep, the routing codes.
And L represents a local interface IP, and C represents a directly connected network.
Right, because the router automatically knows about these. The cables are physically plugged into its own interfaces. It knows the subnet because it literally lives on it.
But the router has to be instructed on how to reach remote networks. The table uses an S to denote static routes, which are manually configured by a network administrator. They define a strict, unyielding path, like to reach network X, go out interface Y.
Exactly.
Now wait. Static routing seems highly secure and perfectly predictable, which makes sense for small, hub-and-spoke branch offices. But are human beings really manually typing in all these routes every time a new server is plugged in somewhere?
Only for very simple networks.
Because the material highlights a critical failure point here.
Yes, a big one.
A static route has zero awareness of the physical topology. If a backhoe miles away digs up the fiber line connecting interface Y to the rest of the world, the static route doesn't self-adjust, does it?
No, not at all.
The router will stubbornly continue forwarding packets into a dead interface, just dropping the data into a black hole until a human being manually logs in and rewrites the configuration.
Which is completely unsustainable for the global internet or, any large enterprise network. That limitation necessitates the final category in the routing table, which is dynamic routing protocols.
Okay, the dynamic ones.
Yeah. In a Cisco table, these show up as codes like O for OSPF or D for EIGRP. Dynamic routing shifts the burden of topology mapping from the human administrator to the router's own CPU.
This is where I want to dive into the mechanics.
Yeah.
Because it's one thing to say they automatically find the best path, but how are they actually doing the math? The source breaks down OSPF, open shortest path first. It doesn't just ask its neighbors for directions, right? It builds a comprehensive mathematical model of the entire network.
Exactly. OSPF is a link state protocol. When you enable OSPF on a group of routers, they begin exchanging link state advertisements, or LSAs. Yeah, and these LSAs contain really granular data about the state of every interface. Whether the link is up or down, the subnet mask, and crucially, the bandwidth of the connection. Every router floods these LSAs until every single router within the OSPF area has constructed an identical synchronized topology database.
So instead of just knowing the next hop, an OSPF router has a complete architectural blueprint of the entire area network.
A perfect map.
And once it has that blueprint, it runs Dijkstra's shortest path first algorithm locally. It calculates the cumulative cost to reach every destination, assigning lower costs to high bandwidth fiber links and higher costs to slow legacy links. It finds the mathematically optimal path, and only then does it install that specific path into the routing table.
And this mathematical awareness is what allows for instantaneous convergence.
Meaning when something breaks.
Exactly. If the backhoe cuts that fiber line, the routers connected to the severed link immediately detect the loss of signal. They instantly generate a new LSA noting the link is dead and flood it across the network.
Oh, wow. So they all know instantly.
within milliseconds. Every router updates its topology database, reruns Dijkstra's algorithm, finds an alternate path through a different geographical route, and updates their routing tables. The traffic seamlessly redirects around the outage without any human intervention.
And then there's EIGRP, represented by that D code.
Yeah.
It approaches the problem differently. It uses the diffusing update algorithm, or DOAL, and calculates its paths based on a composite metric of both bandwidth and delay.
Right.
What fascinated me about EIGRP is that it calculates backup routes. They're called feasible successors before a failure even occurs.
Yes, it's very proactive.
It keeps the backup plan loaded in its topology table, so if the primary link drops, it switches over almost instantly, faster than OSPF can recalculate.
Both protocols demonstrate the absolute genius of modern network design. They create this continuous, autonomous heartbeat of discovery, metric calculation, and adaptation that operates entirely in the background. It's continuously optimizing traffic flows across millions of miles of infrastructure.
It is the microscopic magic that keeps the digital economy functioning. Billions of devices, shifting physical cables, unpredictable outages, and these dynamic protocols are mapping and remapping the globe in real time.
It really is amazing when you think about it.
Which leaves us with a final fallback. If the longest prefix match fails, and the router checks its connected routes, static routes, and dynamic OSPF routes, and it still has absolutely no idea where the destination IP is, it uses the default route.
Represented as 0.0.0000, it is the gateway of last resort.
The gateway of last resort.
Yeah, if a router is handed a packet for a subnet it doesn't recognize, instead of dropping it immediately, it forwards it to the default route. It pushes the packet upstream to a larger provider router, basically relying on the assumption that the upstream hardware possesses a more comprehensive routing table.
It basically passes the buck until it reaches the internet backbone. So what does this all mean for you, the listener? We've covered the deep engineering behind OSI Layer 3. The next time you hit send or stream a video, take just a second to appreciate the absolute symphony of logic happening underneath.
It's quite a symphony.
Your host device is querying internal routing tables and selecting interface metrics. It's wrapping data in streamlined, fixed byte headers and stamping them with a time-to-live failsafe. It identifies the local gateway doorway, and from there, autonomous routers exchange link state advertisements. They're calculating Dijkstra's algorithms based on bandwidth metrics to dynamically negotiate the best possible physical path across the globe.
Right.
Ignoring severed wires and congestion, all in the time it takes you to blink.
Understanding the mechanics of Layer 3 fundamentally transforms how you view the digital world. Instantaneous is actually millions of complex algorithmic decisions executed in perfect sequence.
And I want to leave you with one final provocative thought to mull over based on the implications of this source material. We discussed how IPv4 address depletion forced the industry to adopt NAT, right? Hiding multiple internal devices behind a single public IP address.
Yep, the mailroom analogy.
While it caused processing latency, it inadvertently created a paradigm where your laptop, your smart TV, and your phone were effectively hidden inside the private address space of your home network. They were walled off from direct inbound routing from the public internet.
Which was a side effect that consumers, and even some administrators honestly, mistakenly began to rely upon as a rudimentary form of security.
But IPv6 provides 340 undecillion addresses, which means NAT is structurally obsolete. Every single device in your home, from your workstation to your smart fridge to your interior security cameras to your baby monitor, it's being assigned a direct, globally routable IPv6 address.
Meaning anyone on the outside can theoretically path directly to it.
Exactly. If the technical necessity for NAT is completely removed, and every device possesses a permanent global address capable of direct end-to-end routing, what does the true end of hiding behind NAT mean for the future perimeter of our digital security and personal privacy?
If the private internal subnet ceases to exist, the boundary of what we consider a protected local network requires a complete architectural rethink.
Think about that the next time you hit send. Until next time, keep diving deep.